We're going to take a look at an example where we use both the left endpoints and the right endpoints to be able to approximate the area underneath of a function bound by an x-axis. So we have this pretty basic function, 3 over x, and we're looking at the interval from 1 to 5, and we're going to break it up into 4 rectangles. Right? Now, let's start with the left endpoint. All right, and the diagrams are given for us very nicely. All right, now in subsequent examples, we might have to find the diagrams for ourselves or compose those. So the first thing we'd like to do is anytime you're given one of these types of Riemann sums, the first thing you're going to start with is delta x. And delta x is given by the formula b minus a over n. Well, in this case, b is equal to 5, a is equal to 1. All right, and we get that right here, all right, from the 1 comma 5. And then clearly n is equal to 4. And so this is going to be 5 minus 1 divided by 4, which just ultimately ends up being 1. And so just to make sure we understand what delta x is the base of each of these rectangles. Right? So this is delta x, and 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 this is delta x. And I think everybody can clearly see that to go from 1 to 2, you just add 1. To go from 2 to 3, you add 1. To go from 3 to 4, you add 1. To go from 4 to 5, you add 1. All right, so basically delta x is just whatever the number is that we need to add to go from one endpoint to the next endpoint. But we do need delta x to be able to work with our formula. All right, so that helps us a little bit with whatever trying to figure out the base. Okay, so the base of each of these rectangles is delta x, which is 1. Now, we're going to start with the left endpoint. Okay, so I'm going to get rid of all of these in the left endpoint method because delta x is the same for both the left and the right endpoints. So now using the left endpoint, our values, we're going to start at 1. Okay, so with the left endpoint, you start with the leftmost point. So x is going to be 1, 2, 3, and 4. And we stop because we want 1, 2, 3, 4 partitions. Let's figure out what each of these rectangles, the area is going to be. And I'm going to denote this as A1, and A2, and A3, and A4. Because we have 4 rectangles, right? So we're going to have base times height. And we know that the base is just delta x, and the height is the height of the function at that given point. Okay, and this is when x is 1, x is 2, x is 3, and x is 4. All right, so base times height, base is 1, and the height is going to be 3 over 1. Remember, our function is 3 over x, all right? And that's just going to be equal to 3. Our second area, base is 1, the height is 3 over 2. All right, so I'm just using 2 there, and that's going to be 3 halves. Area 3, base is 1, and x is 3, so we're going to have 3 over 3, which is going to be 3 over 3, or just 1. And then finally, area 4 is going to be 1 times 3 over 4, which is 3/4. All right, so now what do these numbers represent? 3 3/2, 1, and 3/4. Well, those are each of the areas of the different rectangles. All right, so if we go back to our diagram, this first area right here is 3. Right, so we got that right here. The next area is 3 halves. This area is 1, and this area is 3/4. And doesn't that make sense? Each time, the areas are becoming smaller because the function is decreasing. How do we get the total area? Or in other words, the Riemann sum is going to be equal to 3 plus our 3 halves plus 1 plus 3/4. All right, and then we just go right in our calculator and clear this out. So we have 3 plus 3/2 plus 1 plus 3/4. And if it doesn't give us an exact number, we're just going to use math enter or a nice integer value. So it's either 6.25 or 25/4. Okay, so either 6.25 because it's exact, which is really 25/4. And what is this? This is the area using the left endpoint. Of course, that's only half the problem, because the other half of the problem is going to be when we take the right endpoint. Right? So I'm just going to copy this image. Right? So now what we're doing is we're looking at this diagram. And in this diagram, we're going to start at the right endpoint. So notice we're starting at 2, and then we have 3, and then we have 4, and then we have 5. All right, so x is going to be equal to 2, 3, 4, 5. And again, this is for the right endpoint. Right? So we're going to use the exact same formula. So area, which is equal to delta x sub I times f at x sub I. All right. And each of the x sub i's are going to be 2, 3, 4, and 5. All right. So we have like x1, x2, x3, x4. So x1 is 2, x2 is 3, x3 is 4, and x4 is 5. All right, so that's what x sub I times f at x sub I means. All right, I is just the index. In other words, which of the different rectangles are we looking at? So A1 is going to be equal to base times height. Now we know that delta x sub I is 1. In other words, the base is going to be the same for each of those. And then we're going to get 3 over the first x. And the first x is when x is equal to 2. And we already know that that's 3/2. For area 2, that's going to be 1 times 3/3. And we already know that that's 3. For area 3, that's going to be 1 times 3/4, which we already know to be 3/4. And then finally, for area 4, that's going to be 1 times 3/5. All right. To get the Reimann sum, we're just going to add 3/2 plus 1 plus 3/4 plus 3/5. And so when we go back up here, we're going to find out what each of these areas are. Okay, so let's just make sure we understand what each of these numbers represents. Okay, so this is our 3/2, and this is 1, and this is the area 3/4, and this is the area 3/5. And we're going to use those areas to approximate the Reimann sum. All right, so we just go back. And we're just going to add these up in our calculator. Here's a pretty slick trick that we can use. We can hit second enter and then second enter again. And remember where we had this 3 all the way at the beginning? We could just delete that because we're just reusing all the points except for 3. So let's just delete that. We don't have to retype it. And then at the end, we're just going to type plus 3/5. All right. And we get 3.85. Or we could just use math enter and 77/20. All right, so those are pretty big disparities. All right, so we got 3.85, which is really the same as 77/20. All right, now again, that's the area under the function f at x equals 3/x using the right endpoints. All right, and clearly that's different. Okay, so if we go back up, right? So what we can say is, just even looking at the diagrams, we know that this is an overestimate. From the previous video, remember the right-hand estimate, the left-hand estimate was an underestimate. Okay, this one's an overestimate. And this is going to be an underestimate. All right, so that's how we can just go through and approximate the area. And the true area is somewhere between 3.65 and 3.85, or 6.25 and 3.85, excuse me. So just to give us some room and just to make sure we all understand what's really going on with this, the true area is somewhere between 3.85 and 6.25. All right, but that's a pretty big disparity between those two numbers. So is it 3.95 or is it 5.55 or whatever it is? We don't know yet. Now, later in chapter 5, we will be able to figure that out. So we'll do one more example that kind of ties everything together. And in the next example, we're going to have to generate the diagram for ourselves and just go from there to be able to approximate the area underneath of our